I want to talk today about how do we guide the system design conversation. How do we guide the conversation in a way that touches all the most important aspects of system design? So let's say, for example, we're talking about our two-stroke engine project. So we have, for example, we have a engine API that we're routinely calling 5,000, making 5,000 requests per minute. And our conversation is around how do we address the scalability problem of this? How do we address the fact that we're receiving intermittent errors when we call our endpoint? And we are receiving intermittent errors due to the fact that our API is running out of resources. This is the problem, and we need to address the problem, but we need to guide the conversation so we hit really all aspects of the system design before we are directly asked about them. So one way we could do this is we could go about it two ways. We could directly address the problem in the most straightforward way possible. We could say, okay, let's just vertically scale our instance by adding memory, maybe hosting it on a larger server or wherever it's hosted. Vertically scale it. That will automatically free up enough resources so we minimize however many intermittent errors that we're receiving. We can minimize those. We're not going to address the scalability problem in the long term with this solution, but in the short term, it'll at least bring down the error rate, hopefully to none, once we scale that up appropriately. But once we've done that, we really need to address the horizontal scaling issue. How do we fix this from a long-term perspective? But not just horizontally scale in the context of, okay, adding multiple instances of our service, but how do we think about it in the broader context of a system? How can we bridge the gap of connecting our front end to the back end in a way that's a little bit more scalable? And to do this, we can introduce queues. And so if we introduce queues, we can now publish a message to the queue from our front end as opposed to try to call and wait for a response back from the backend API all the time. So let's add a queue in there. And when we add a queue, let's go ahead and add a retry policy into this. So that way we can add a retry policy on the backend API so that in the event that that API is unable to process that message, we know that that data is going to be preserved because our queue, in this case we can make it RabbitMQ as a message broker, is not going to receive that confirmation acknowledgement, so therefore it's not going to remove that message off the queue. So we have that reassurance that we can always maintain data quality in the event of an error. And once we establish our queue, our retry policy, and correct error handling by way of, let's say, adding an error queue, or you may call it a dead letter queue. Once we have all those components in place, now we can begin to address the actual logic on the API. How do we make sure that we're not creating a bottleneck on the consumer of our queue? A couple ways we could do this is if we have to make repeated, in this example, we have to make, let's say, we have to make two database calls, and then we have to send it, we have to actually send it out and save it to a database, another one. So we have to make two database selects, and then we have to do an insert statement. So we have to look at this. We have to look at the selects. We have to ask the question: is it possible to operate or to run those concurrently? Can we take advantage of any of that? If it's not possible, meaning that one select, we might need like something from the previous select to filter on. If it's not possible, then we can't do it. But if it is possible, let's run those concurrently, and we could save a little bit on time. Hopefully, bring down our total request time. Once we have that data in place, we have to figure out, okay, how do we insert that data to the database in a non-blocking way? Because if that database is experiencing a high load, we may introduce some slowness. So one way to do this is introduce another queue into this, send that data or publish that data up to the queue, and then the API can then move on. And if we have it set up, we can get a confirmation that it was received by RabbitMQ, and we know that it's in there. Then we can introduce maybe another service independent of our engine's API that can just be a consumer of those messages on that queue that can then take those and publish them into or insert them into our database. So that we have this chain of data flowing and nothing is waiting on anything. The only thing that we still maybe have to wait on are those two select statements from the database. So that could still be a potential bottleneck depending on how expensive those SQL queries are. If we're doing a lot of joins, a lot of full table scans, then it could be problematic. So we have to, I think, first do benchmarking on those queries to see, okay, do they take 100 milliseconds to run, or are they taking 2 seconds to run? Very big difference. So I think we have to act accordingly. But in this example, I think that since we've already broken out the insert into its own service, we can just assume, I'm going to assume that those two select statements on the database are not expensive operations, they don't take a long time. So that's my assumption going into this. So we're going to move on. So now we've created this flow up until our insert into the database. So now our API knows that data was published through our exchange to our queue in RabbitMQ. Now we know that, okay, we've done that. Now we need to send some kind of response code back to the front end just as a confirmation. So we're just going to return a status OK 200 from our .NET API. Now the front end is still wanting to know that data was inserted correctly. And part of what we needed to do actually is when we take that data and insert it into the database, we want to know exactly what time that was, because our engine is running and we need to have direct timestamps as to when that data was saved, just to help us log things later. This is purely hypothetical. But for whatever reason, in this case, we need to know the exact timestamp and also grouping of how many database rows have a similar temperature as to the one we just inserted. So we're inserting engine details into the database. Part of those details are engine temperature, and again, the timestamp of when that snapshot was taken. So we need to return a grouping by temperature, and also select the timestamp for each of those. So what we need to do is when we insert that into our database, if we want to leverage the same service, we should be able to, because it shouldn't be that much to add an additional select after that insert. Again, depending on how we have our indexes set up. So one possible way, and we'll just introduce this, we can refactor it as we go, is to add a select statement to get that proper data back. We can do a select, and then we can send it down to our front end, but we're going to use WebSockets to do this. That way the front end is not blocked by that at all. So that way when we know we inserted it, we can send a real-time update down to our front end using WebSockets, and the front end is going to be immediately notified of a record was inserted, and here is the grouping of data that belongs to. So if we're adding another record that belongs to the group of data that has temperatures of around 400 degrees Fahrenheit, we can know that a record was inserted that fits into that group, and then we can catalog it basically on the front end. But now we've connected a way where we can have real-time updates or notifications sent to the front end, sent from the back end to the front end in a completely non-blocking way. We could even refactor this more if we want to separate out that select into, again, maybe some kind of queue if we want to do an insert first and then send a message up to a queue and then have another consumer off that queue to be notified of that message to then do the select. We can do that, and that might be a little bit more scalable depending on how much data that we have. It may be, I don't know, the performance might be negligible in terms of the the benefit we get from doing that, but I think we'd have to experiment. The other thing that we could introduce on the front end, if we're routinely doing these calls to get all this aggregated data, we could introduce some kind of caching layer, whether that's going to be just a call on the back end to a Redis cluster to try to do a cache hit, but if it's a miss, then go and get the data. We could do that. I think we could probably set up our front end, our running engine, if we need to get if we're pulling data into a table, to first say, okay, do we have cache that we can go and hit based on whatever key we're trying to get it by? Again, purely hypothetical, but we need to add some kind of caching layer so our front end is not always making these expensive back end server calls, right? That could bog down our system depending on how many users we have. The next thing we have to, I think, bring into this conversation is that, okay, we've done a lot of the system design parts, but how do we address the horizontal scalability aspect of this? So if we want to add multiple instances of our services, we need to be thinking about what happens if service A is updating a record in the database that service B is trying to get. So we have to introduce some form of locking. We could do this with distributed locks, and depending on what database you're using, in our case, it's going to be MySQL. MySQL supports distributed locks, so we could get away with that. And then we could have service A and service B both trying to acquire a lock. And if service A has already acquired it and service B can't acquire it, then we can just have some kind of either waiting period or something else. But we have to make sure that regardless of what happens, those locks are released. So we could put them in some kind of finally block at the end of our logic to always be released. But we have to experiment with that, because we have to make sure that we don't introduce a deadlock scenario into our system. But we also want to make sure that we're not introducing more complexity maybe when we don't need to. And if we can get away with maybe adding replicas of our database, so we're not accessing the write instance, but we're instead accessing the read instance for select operations, then we should explore that potentially first before we add distributed locking maybe in some parts. Now, direct inserts, I think we either need to do wrap it in a transaction, or take it a step further and I think introduce some kind of locking mechanism if we're not completely satisfied with transactions. And if you're working in a SQL Server environment, you could experiment with distributed transactions, depending on how complex your queries are getting and how many tables you're trying to access in databases. But that might get a little bit problematic depending on how big this thing is going to get and how really how easy you want to be to debug. But we have to, I think, experiment with transactions and introduce them where we need them. So if we're doing any kind of inserts where we need it to be rolled back, then we should introduce transactions. And another aspect to scalability is we need to make sure our Redis cluster also is scaled, so we have multiple nodes running. And then once we do that, we have to figure out a data sharding strategy. People use the modulo function as a way to do this. That would quickly categorize it. But if you're working with data that has high cardinality, you should be able to create better data sharding compared to if your data is just like, ones and twos, right? Because then you don't have much data. You're going to spam two nodes of your Redis cluster compared to if you perform some kind of modulus function where it might separate them out. Because what we're trying to achieve with sharding is we don't want to send all of our data mostly to one node of a Redis cluster. We want to evenly distribute it out, so that way we achieve faster performance. There's different algorithms we could explore for this, but one approach would be the modulo function, so we could talk about that in our conversation. Another aspect of this is what happens in the event of a system failure. And so this will bring the conversation back to queues and why queues are absolutely necessary in a system design, because queues prevent or help to prevent against some kind of data failure or complete service failure. If service A, our engine API, goes down, all of our instances go down, but we had sent data to a RabbitMQ server, that data is going to be there, and it's going to sit there until it's consumed off of that queue. And if we take the approach of, okay, we can introduce queues wherever we need them to help mitigate against data loss in the event of total service outages. But how do we prevent against the loss in terms of if our RabbitMQ broker goes down, if that server goes down? We have to set a couple configuration settings. We have to make sure our queues are durable, our message delivery mode is persistent, so that way in the event of a server outage and then it gets brought back up, our queues are still there and our messages are still there waiting to be consumed. And we also need to make sure that if we are in a truly distributed environment, that we have highly available queues set up, so we have a cluster of nodes running in our RabbitMQ uh, environment. Now we have a cluster of RabbitMQ servers. So if we have multiple queues now, let's say we have our engines queue, now we have 3 nodes running of that, so we have 3 different queues. We have to make sure that that data, we're not getting repeated messages, which can be a problem, and we also have to make sure that we're not introducing any kind of data inconsistency. Because if one instance of engine API consumes from one of our queue nodes, what happens if another instance of the engine API somehow accesses that same data? And so this can introduce the problem of duplicated messages. And there's a couple strategies to take care of this, like federated data and shoveling. You can look those up, but there's a couple. This again introduces more complexity. And whenever we talk about distributed systems, we have to think about these problems, and these are not simple problems to solve, and they can be very difficult, because duplicated messages is a legitimate problem with, again, just a distributed system, and specifically queues. We have to make sure that if we do receive a duplicated message, that we have the appropriate checks to make sure that regardless of what message comes through, that the same action, this same operation can be performed with the same result, regardless of what message it is. So because the service shouldn't matter what is being sent there, and it should respond appropriately. So we have to either add, I think, logic to check for, okay, is this is this a duplicated message? And we can do that potentially with some kind of message ID, a GUID or something like that. We can do that with message headers from RabbitMQ. We can do that with like some kind of, I'm trying to think. It's not an easy problem, and I think it requires experimentation. But for the context of the system design conversation in terms of how we guide it, I think just introducing the complexities around this would be good, because it brings up a lot of concerns and problems that you may encounter when talking about these things in a conversation. And I think finally, one where we can end it and bring it back to is the overall experience on the front end, because that's really what matters at the end of the day, is what is the product doing? What is our engine? How is our engine performing on the front end? Is it able to run despite what's happening on the back end? Is there no lag? Are we seeing updates of something? It can be error updates. It can be the real-time updating of the temperature. It can be, whatever it is. We need to make sure that somehow is still functioning to some degree, regardless of what is out on the back end. So we need to have some kind of detection of that, so we can introduce some form of health checks to say, okay, we are noticing a true outage, so we need to either try to automatically bring that up through some form of automation, but we also need to notify the front end of there may be some kind of um, if it's a critical system error, I think we should have to notify the front end of like, hey, there's we may you may have a limited experience. We're going to cut off these features that connect to this service, because you don't want the user to receive a error message on the page, like just a blank page, and they see an error message like a 404 or whatever it is. That we don't want that to happen. Well, we need to be as proactive in terms of, okay, if we do notice one of our services is down and one of our features we know connects to that service, we need to switch that feature off before the user is able to see that error and say this is unavailable because this our system is totally down. And this is like an extreme edge case, I think, because we'd have to have all of our engine APIs down, and that would be a big problem, because now we're not getting updates in terms of what the engine performance is. But I think that we have to respond appropriately on the front end, and to make sure that to the user everything appears functional still to some degree, right? The core things are still there, and the user experience is not, has not been neglected, despite what is happening on the back end. That's the challenging part, and I think that part requires a an extra step at the very end of the process to say that, okay, can we purposefully bring down some of our services and then see what happens on our engine front end? And then once we do that, we can know, hey, what do we have to put in place to make sure that we don't receive legitimate error messages? And I guess we could end it here. If you want to tie it into load testing, you could talk about, once we have all this in place, we could introduce load testing, with Postman or something. We could just send, millions of messages through our system. We could send millions of engine data points through our system and see what happens, see if it truly is scalable, and start to identify bottlenecks and start to get metrics around producers and consumers of the queues, and see, okay, is a queue actively backing up in size, or is it growing because the consumer is not able to process the messages in time, therefore creating this leak on the queue because it's never going to be consumed. That might happen, and that's something that we need to be mindful of, particularly if we ever have a consumer that is connecting to a database, because that can pose problems, and that can be trouble. That can be asking for bottlenecks, and we saw it happen on our engine API, which is one of the reasons that we introduced Rust to act as the consumer, because it's a little bit faster and we're able to process data a little bit faster, but still maintain some of that the flow of data without causing a backup into the queue. So you may need to get creative with languages you try. You may introduce Rust into your system because it's very performant, it's very memory safe. And I think that this is where some of the creativity comes out. Once you establish the baseline fundamentals of what your system, what you want it to do, you can begin asking the question of, can we make this better? Can we introduce something in a different language that maybe we hadn't previously thought of? And Rust is one way to do that. In .NET, you could exploit some features. In F Sharp, you could introduce. I'm convinced that queues, if we really want to get creative, we can get really creative in terms of how we structure our exchanges, and how we fine tune the settings of, let's say, prefetch counts to make for better experiences. Because if we're trying to fetch too much data right off the get go, I mean, we need to tune that to be a little bit more performant. But it's that truly is a game of trial and error. You'll have to just adjust that as you see fit. But maybe if we need to squeeze a little bit more performance out, maybe we don't need publisher confirmations. Maybe because that'll make it faster. Maybe we don't need Um, Maybe we don't need all these headers. Maybe we don't need these complex routing keys. So there's things that we have to be mindful of, because every millisecond we add to latency is gonna create a potential bottleneck somewhere in our system. So hopefully, just thinking about how do you guide a system design conversation is on your mind, because I think that really the crux of system design conversations is not asking the right questions. It's knowing how to think through conceptually the flow of data and what happens at each step, and being able to map this in your mind and create a model based on one question, or wherever that question may land. If it starts at the database, we can construct it backwards. If it starts at the queue, we can construct it out from that. Hopefully, this is helpful, because I think it's important that we get better at talking about this, because I think it helps for creative problem solving if we understand systems limitations, and what can help alleviate that. Obviously, there's so many more things that we could have talked about. There's so many unique technology choices. There's so many very creative ways you can do this in code, but there's a lot left out. But obviously, just start thinking about it. And yeah, if anyone has any thoughts or general, you know, ideas, maybe how to expand this type of conversation, let me know. I'd be interested to hear. So anyway, thank you for watching. I'll see you in the next one.